So for this last video of chapter 1, I think it's actually the last one this time, we're going to talk about section 1.5 from the text, which is about expressing quantities in engineering notation. So before we do that, let's just actually review the metric prefixes that we need to know as engineers. And they're actually kind of tabulated here to the right. If we need to scale a unit up by a factor of 1,000, meaning that the unit itself is just way too small and we need to work with a bigger bundle of it, we can use the prefix of kilo, which is nothing more than taking a unit and multiplying it by 10 to the third. So in that case, if we were to have something like kilometers, 1 kilometer would just be 1,000 or 10 to the third meters. In the same case, we could do 10 to the sixth, which would be mega, 10 to the ninth would be giga. And in addition to making a unit larger, we can actually make it smaller by scaling by these prefixes, which are 10 raised to negative power. And the three that we traditionally remember are milli, 10 to the negative third, micro, 10 to the negative sixth, and nano, 10 to the negative ninth. So why do we need this? Well, if you think about that first lecture that we did, where we talked about all the different scales for which statics applies, are really all engineering applications, we're going to need to adjust the physical size of our units. And whenever we're in the SI system, we're going to be able to do this using by adjusting them by a power of 10 and just writing a prefix for shorthand. Now, why do we only kind of memorize these multiples of 3 in the power? Well, that's related to this idea of engineering notation. So if you always have your prefixes as multiples of 3 in the power, you're going to be able to always write the coefficient or the actual amount of the quantity in the unit as a number between 1 and 1,000, not inclusive of 1,000. Of course, if you had 1,000, you could take another factor of 10 to the third and absorb it in the prefix. Other things that are important to know about the actual units, helpful hints from the text. When you have multiple of a unit, like 5 kilograms, you just write it as 5 kg, not 5 kgs. You don't make it plural. When you have units that are products of one another, like meters times second, you actually use a little dot between or a multiplication to denote that it's a complex product unit. In addition, the majority of the time, the units are going to be lowercase unless it's something named after someone like Newton, Pascal. In addition, for prefixes where there's multiple that start with the same letter, like milli and mega, we'll make the ones that are larger have a capital letter, mega 10 to the sixth and giga 10 to the ninth. In addition, if we have the same unit multiplied it by itself, like something describing an area, in that case, we would use a actual power to denote that a centimeter squared means a unit that's a centimeter by a centimeter. And in general, we won't use compound prefixes. What that actually means is don't use like kilo times kilo, use just mega in that case, if you have two factors of 10 to the third. And always good when you're working problems to not mix between the FPS system and the metric system. So in terms of speaking of significant figures and engineering notation, we have, when you think about writing a number in engineering notation, it's just going to be a number in scientific notation, where the actual exponential term, the power of 10, is a multiple of 3. And that will allow the coefficient, as we discussed, to always be between 1 and 1,000, inclusive of 1, but not inclusive of 1,000. So the real reason that writing a number in scientific notation or engineering notation, which is just a special subset of that, makes a lot of advantage is it allows you to clear up ambiguity about how many significant figures are associated with a number. And remember, significant figures are just a measure of how precise the actual number you're reporting is. If I tell you there's 1,400 of something, you might not know offhand, well, did he round that? Or is there actually 1,400 of them? Scientific notation allows us to take out the ambiguity of that. If I tell you it's 1.4 times 10 to the third, you know there's two pieces of significant information, two significant figures. If I tell you it's 1.400 times 10 to the third, you know that there, in that case, are four pieces of significant information or significant figures. So when you have that number 2,400, it's just hard to tell. So usually within our text, the book will ask you to just report a certain number of decimal places, much more common within my engineering. But know that the motivation behind that is if you report just a ton of decimals that you read out of your calculator, they're not going to be physically meaningful for the majority of actual quantities that you can measure. So it just kind of looks funny. However, when we're actually, here we want to get a good grade, we're entering the answers into my lab, you don't want to round your intermediate figures. Let the actual calculator do its work and store those intermediate answers to the highest level of precision possible, and then just round the final answer. So how would you actually do an example here? What if you had 52 slugs per cubic foot? Well, hopefully you remember a slug is just the unit of mass in the FPS system, and foot, of course, is a unit of length in the FPS system. If you want to convert it to SI units, you got to find your conversion factor for slugs to kilograms, which is the SI unit of mass, and feet to meters. And if you actually go and look up on our table, probably no one would remember this. Oftentimes people remember that a foot is about 0.3 meters because usually everyone remembers how many centimeters are about in a foot because of a ruler that you probably saw in school. So with those two conversion factors, it's just going to be a matter of chaining it together and getting rid of the units that you don't want. I don't want slugs, so I'm going to put slug in the denominator. I'm going to use my conversion factor, 14.59 kilograms per slug. Put that in the numerator. And remember, when you do this kind of chain dimensional analysis, you can cancel units just like you would cancel common factors. One thing you want to be careful of here when you're trying to convert from cubic feet to cubic meters, remember that conversion factor, 1 feet per 0.3048 meters, the whole thing needs to be cubed. And that's going to make this 0.3 number quite a bit smaller. So if you carry through the math there, what you'll see is it's 2.679 times 10 to the fourth kilogram per cubic meter. Now, why isn't that a good thing to write? Well, if you think about it, 10 to the fourth, well, first of all, as engineers, we don't like 10 to the fourth, right? We want to use the 10 to the third there to have kind of a multiple of 10 in the power. But even if we made that 10 to the third, even if you took 10 to the fourth and took the 10 out, absorbed it in the coefficient and put a 10 to the third here, you'd have those kind of stacked prefixes again, kilo times kilo. And remember, you don't want to do that. Whenever you have two prefixes, combine them together and just get one. And 10 to the third times 10 to the third, your exponential rules. When you have like bases, add the power, that becomes 10 to the sixth. And this actually becomes 26.8 megagrams per cubic meter. So I didn't lie that time. That actually was the last lecture of the first chapter. Just a refresher, hopefully we'll get textbook access very soon, and we will start working on chapter 2, which actually has the first homework associated with it. So have a good evening. I'll talk to you soon.